Jai Hind everyone, myself Ankita, faculty of Department of IT, AKGEC. Today I am going to discuss adversarial search from the course BCS 701. It is a course that will be taught in 7th semester. So I will be discussing the introduction to adversarial search, Minimax Algorithm and alpha beta pruning. So basically, with AI, we are trying to solve various problems. For that, we are formulating our problems as search problems. Now, for that, we are dividing different types of algorithms that are able to solve those search problems. The first one was that we have known, that is uninformed search, in which we have algorithms like BFS, DFS. Then we have informed search techniques, where we have best first search and A-star algorithm. And then we have local search algorithms, in which we study hill climbing algorithms as well as simulated annealing algorithms. Now, another class of algorithms known as adversarial search is there. Now, in contrast to the previous three types of algorithms, in adversarial search, we have multi-agent environment. It means that we have more than one agent present which is trying to achieve their goals. And interestingly, the goals of these agents are in conflict. So we can say these are working in competitive environments. So these multi-agents are working in competitive environments and their goal are in conflicting in nature. So which this gives rise to an adversarial search problems, which is also known as games. So it is quite interesting that our AI researchers are more interested in making agents which can play these games. The reasons are very simple. These games are very good reasoning problems. They are formal. They have set of rules that we want to we follow to win the game. Also, it's non-trivial. We have to use our mind and different reasoning techniques so as to win the game. Also, it is direct comparison. We can compare our programs, our agents with the humans by let them play with the humans. For example, the games like chess, like Go, right? So which kind of games we should play? We cannot, in the adversarial search, there are specific set of games that we want to solve through our agents. The games will have these characteristic features, that is, they have the sequences of moves to play. So they will be multi-agent environment and obviously they will have sequence of moves. Also, they should have rules to specify the possible moves. So there are set of valid moves and we have to follow those valid moves so as to reach the goal. Third is, the rule is to specify payment or reward for each move. So for each move, a payment or reward is being associated. So if it is a good move, it's an optimal move, the payment or the reward will be given. And if the move is not optimal, we are, reducing the reward. Second is, and our main objective is to maximize our reward. So main purpose here is to maximize our reward. So in adversarial search problems, first we have multi-agent and multi-agents. Second, we have competitive environment, and the objective, or we can say the goal node, is to maximize our payment reward. So we can say such games can be written as deterministic turn-taking two-player and zero-sum games, right? So here our environment will be fully deterministic, fully observable, in which we have two agents which are acting alternately with each other. And obviously, the utility values at the end of these games are always equal and opposite. It means if one agent is getting +5 as an utility, the other agent will getting -5, and therefore it's called as zero-sum games. That is, and at the end we will get 0. So when we try to depict two-player games, it is like this. First, we have the opponent move, and then when the opponent has taken its turn, then we have to generate a new position. For that, I have to see whether the game is over or not. If it is over, okay, I don't have to do anything. Otherwise, I have to generate the successor. So whatever state I am in, I have to generate the different possible successor. What is that? Means all that possible valid moves that are possible, and then I have to find out the most optimal move. Out of all the valid moves, I have to find the optimal move, and then for that I have to evaluate the successors, and we have to move to the highest valued successor. So if the game is over, then it's over, okay. Otherwise, again, there will be a chance of opponent. So this is how a two-player game actually happens. Now, when we are trying to solve the game problems, we have to describe them in such a way so that our agents are able to solve them, right? So, whenever we are talking for adversarial games, we have two players and we call one player as max and other player as min. The purpose of max player is to maximize its utility and the purpose of min player is to minimize the utility. So therefore, it is called as zero-sum game. Why? Because at the end, your utility will be zero. So the agent that is wanting to maximize the utility will win the race if the utility is +1. Otherwise, if -1, then the min will win. So at the end of the game, the points are awarded to the winning players and the penalties are given to the losers. So a game can be defined as, first, this is your initial state player. If there are two agents, there will be two players. Then what are the actions? What are the possible moves that are possible, that are valid moves? And after that action, what is the result? What is the next state my agent will reach? Then what is the terminal test? It will check whether my game is over or not. So the end of the game is determined by terminal test. That is, if my game is over, the chances are finished. Then utility will tell us what is the utility of the player. So if it's a max player and he has won the game, the utility will be +1, otherwise it will be -1. So the first algorithm that comes is your Minimax algorithm. It is a specialized search algorithm which is used in the game playing to determine the optimal sequence of moves for a player in a zero-sum game involving two players. So here we will having two players and we have to determine the optimal moves for both of these players, right? So usually it uses the depth-first search algorithm. So we are using the depth-first search algorithm for finding out the path where we have all the optimal moves that are being played by both the max player as well as the min player. It also operates recursively using backtracking to simulate all the possible games. So basically what we have in Minimax algorithm, we have to backtrack the values, right? Suppose I have this node, okay, and I have my utility attached to it. So when I'm trying to form a min-max layer, first I will be labeling them the chance. For example, in this level, the max will have the chance. In this, min will have the chance. In this, max will have the chance, right? So in this node, the agent will try to maximize its utility. In these two levels, the agent will try to minimize the utility. And in this tree, the agent will again try to maximize its utility, right? So now these are the utility values. Now these values will be backed up by the help of backtracking algorithms so as to find out the sequence of your optimal moves. So because these utility we are getting to know only at the end of the game. So therefore to find the sequence of optimal move in advance, we have to back up these values upward so as to find out the optimal path. Now, in this, we have two nodes where each select the maximum nodes will select the maximum values, whereas minimum nodes will select the minimum values. So, here at these levels, it will select the minimum values from these two, right? Here, it will select the maximum values of these two, right? Similarly, it is applied in chess, checkers, and tic-tac-toe. So, initially, what we apply, max player will be represented by -. This is the worst possible utility of your max player and this is the worst possibility utility value for your min player. So initially we will keep the utility value as -infinity for the max player because it's the worst value, whereas for the min player we will keep it as +infinity. Now we'll try to understand the Minimax algorithm with the help of this example. Now you can see this is my max level, this is my min level and this is my max level. Right. So we'll start applying depth first search. Now we'll start from here and from here I will move to B and from B I will move to D and this is how the DFS work, that we are going deep into one branch. So from A I will go to B I will go to D, right? So once I reach the D, what I will find? I will find the utility value as -1. What I will do? I will back up this value to D, that is -1. Okay. Then again, I will move over here and I will find out 8, right? So I found 8 and -1. do two values, right? So since this is a max node, what I will do, I will choose this one, right? So I will choose this one. Fine. So here the value will come out to be 8 because I have chosen this, because this is a max node. Now once I have moved here, I will move back, I will again backtrack, and here the value of this is 8, and again I will move to this branch. Now again, following the same steps, I will follow this is -3 and this is -1. Again, this is a max node. So what I will do, I will choose which path? I will choose this path, right? So here the will be -1. Fine. So here my value will be -1. Now, since this is a min node, I will again, so what path I'm following? Like this again. From here, this is my min node. So which value it will choose? It will choose this path. Why? Because this is lesser than these two. So now my current path is like this. Okay. Now only one part of my branch has been explored. We have to explore the different part. So I will come back upwards and I will start moving toward this path, right? So here the value is 2. How it's 2? We will move like this, and here the value is 2. The first it will be 2 and then here it's 1. But since it's a max node, I will choose the maximum value. So it will be 2, right? Similarly, what happens? I come over here. After following all the paths, I come over here and I found the value to be -3 and 4. So since it's a max node, I will choose the value 4. Now here I have got 2 and here I have got 4. You can see here I have got value 2, here I have got the value 4. Now what happened? Since it is a min node, I will choose the lesser value, that is 2. So I have chosen this 2. Right? And in this -1 and 2, which is the maximum value, since it's a max node, it will choose 2. So final path will be like this. Right? So this is how our min-max algorithms work. So when we try to evaluate the efficiency of min-max algorithm, it is complete algorithm. The algorithm is complete and will definitely find a solution if one exists. So since it's a DFS algorithm, it follows DFS algorithm. We can say the algorithm will be complete if the tree is finite. It is optimal. It will always guarantee to find the optimal strategy for both the players, right? But the problem with this min-max algorithm is that it is not able to exploit the opponent weakness against suboptimal opponent. Now here what we are doing, we are assuming that both the players are moving its optimal moves. So this is not always the case, but it is right now it's only assuming that whatever moves the opponent player is taking is the optimal moves. So it is not able to, you can say, exploit the weakness of your suboptimal opponent. Time complexity is same as that of your DFS, that is order of B to the power m, where m is the maximum depth of the tree. Space complexity is also same as that of your DFS. Now, what is the problem of your min-max algorithm? Right? The problem is that the algorithm can be slow for a complex game where we have many possible moves. So possible moves where we have many, you can say, many valid moves. If we have many valid moves, it will be the tree form will be very large, right? So a game like chess can have around 35 possible moves. So at one point, I can have 35 valid moves. So you can imagine the size of the tree will grow exponentially. And obviously, it will have the large number of possible game states. So average game length, if m is equal to 100, means the depth of the tree is 100. The search space will be 35 multiplied by 100, and it will this very huge amount, 10 raised to power 100. 154. So this amount is search space will be very huge. So it will be very much time taking for applying your min-max algorithms in such problems. Now to overcome the problems that we have encountered in your min-max algorithms, we have alpha beta pruning. Now in alpha beta pruning, what happens? In min-max, we have the number of game state it has to examine is exponential. So we have the states that has been created are in exponential in nature. So to reduce the number of states that we need to explore to find out the optimal moves, we have to prune certain branches which will have no impact on the results, right? So we can implement, so by performing pruning, we can eliminate large part of the tree from the consideration. So when alpha beta pruning is applied to a min-max tree, it returns the same moves as a min-max would, but prunes away branches that cannot possibly influence the final decision. So basically, alpha beta pruning will give you the same result as the min-max algorithm, but in lesser time. Why lesser time? Because we are able to prune the branches that are not necessary for us to visit. Why? Because they won't have impact on our result. So alpha beta pruning is basically an optimization technique of the min-max algorithm. It significantly reduces the number of nodes that need to be evaluated in the game tree without affecting the final result. So alpha beta pruning skips this evaluation of certain branches. So what happens that it skips those branches which we won't have any effect on the result. For that, it has, have two parameters. It has created two more parameters, that is your alpha and your beta. So alpha and beta pruning get its name from these two parameters, and alpha is the highest value, or we can say best choice that we have found for our max node. So we can say alpha is the best choice we have found so far for the max node, whereas beta is the best choice we have found so far for the min node, right? So also we can say alpha is a lower bound on the value that a max node may be ultimately be assigned. So it's a lowermost value. So you can say the best, best choice that I have found so far, or we can say it is a lower bound on the value that a max node may be ultimately assigned, whereas beta is the best choice for a min node. So it is also, we can say, it is an upper bound on the value that a minimizing the node may ultimately be assigned. So what happens? Alpha beta search updates the value of alpha and beta as it goes along and prunes the remaining branches at the node. So it will start with the help of your values of alpha and beta. We are able to prune the values of branches. So we can say if for the current alpha and beta, I am getting the worst value, then our current value for alpha and beta, I will prune them. Now, what are the various points that we need to consider for the pruning? First, the alpha starts with a minus infinity. It is the best value for a max node. So, right now we start with minus infinity, and the beta is the best value for your min node. So, here the value is infinity. So, it is the worst value right now. We started off with the worst value. So, when we have to prune, a branch is pruned when maximizer best option is less than maximizer best option alpha. So, if minimizer best option is less than maximizer best option, that's alpha, we prune. So, in short, we can say if we are finding a condition where alpha, the value of alpha is greater than or equal to b, we will prune the remaining branches. So, each node has to keep track of its alpha and beta values. For each node, we will keeping track of alpha and beta values, and alpha will only be updated in the max terms, whereas beta will be updated only in the min terms. So, very good. For example, I have these nodes, right? So, for this is my max nodes, these are my min, this is my max. So, in this, I will be updating my alpha values, and in this, I will be updating my beta values. And I will prune the branches once I will get the value of alpha is greater than or equal to beta. These are the 3 points that we need to consider. And the node values will be passed to the upper node instead of values of alpha and beta going to the reverse of a tree, right? So, we will try to understand this with the help of an example. So, you can see we have A, B, C, D, E, F. This is my max level. Here, our max player will choose the move. In this level, our min player will choose the move. In this, my max player will choose the move. This is my terminal nodes which will tell me the utility, right? In the beginning, my alpha will be minus infinity and beta will be infinity. Now this is the worst value of a max node and this is the worst value of a min node, right? So what we'll do, I'll start applying your DFS algorithm. I will start over here. I will move over here. When I move over here, you can see this is my max node. So the value of alpha will be updated. So when the alpha will be updated, the value of alpha is 3. Why? Because out of 2 and 3, 3 is more, so value of alpha will be updated. And beta will remain same, it is not getting updated, right? Now, similarly, I will move over here. Here, the value of beta will become 3. Why? Because this is a min node, this is my min node, and here the value of beta will be updated. Now, the value of beta will be 3 from this because I have explored only one set. So, here the value will be right now 3. Okay. Now, what happens? After exploration of this, here the value of beta is 3. I will come over here. I will explore my next branch. Now, since this is my max turn, what I will do, it will move to this. So, here it will move to there. Now, here the value of alpha will be equal to 5. Right? Here the alpha is equal to 5 and the value of beta is 3 over here. Fine. Here the value of beta is 3. Here the value of alpha is 5. Right. So, what we can say, we have to see whether it is necessary to explore this branch or not. So, you can see since this is my min node, it will always select value of 3 or lesser. Right. It will select. It will always be this at this min node, this node will, since it is a min node, it will select value of 3 or 3 say lesser. Okay. Now, what I am getting from this node, since it is a max node, right? Now, this is a max node. So, it will select 5. It will select minimum value of 5. Right? It will select if it can be more than 5 also or less than 5. This could be more than 5 or less than 5. In either way, it will at the minimum will select 5. Now, it won't go beyond 3. Why? Because it is a min node. It has also already get 3 from this branch. So, it won't go beyond 3. So, here the value of alpha is more than beta. So, here there is no point in exploring this branch. Why? Because since it's a min node, it won't go beyond 3. Why? Because it has got 3 from this branch, right? Now, what is the point of exploring this when I am getting 5 from this only? So, 3 says it won't go less than 3. So, there is no point in exploring this branch. So, we will prune this. Fine. Again, I am going to explain. First, I have moved over here. Here we got the value 3. Because I have explored only these 3 from this branch, I am assuming that I will get my cost as 3. That is the minimum cost, right? Now, from again, when I started exploring this branch, now what happened? I got 5 in first branch of E. Now, it says that I updated my value of alpha as 5. Now, the value of this alpha is greater than beta, right? Now, what happened? Since it's a min node, it will never choose 5. Why? Because it has already get a value that is lesser than 5. That is equal to 3. So, there is no point in moving further to explore this branch because whatever it value, if it has got value suppose 3. So, even if we have explored, what happens? Alpha ki value 5 rahegi. Now, when alpha value is 5 and here beta is 3, so obviously since it is a min node, it will choose 3 only. Fine. And if the value is 9, even if we have explored this, the alpha value will be 9. Okay. So, when it's 9, again, since it is a min node, it will never choose this branch. So, there is no point in exploring this branch. Okay. Now, what happened? We have pruned this. Okay. Now, here the value that has come has found as 3. We will move forward and here, now from this branch, I am getting the value as 3. So, I have updated my values alpha is equal to 3. I again move through this. Now, since it is a max node from 0 or 1, it will choose 1. Now, here the value of beta is equal to 1. Fine. And here the value of alpha is equal to 3. From here we can say the value of alpha is equal to 3. We have got from here, right? And here the value is beta is equal to 1. Fine. So what happens is, it is a min node, it is getting the value of, getting the value of beta is equal to 1. And what happened? Since it is a min node, whatever you will get, here we have already get the best, alpha is equal to 3. And since from this branch I have got the value as 1, so whatever be the cost of these branch, it won't go beyond 1. Because it is a min node, it won't let it go beyond 1, right? So it could be 1 or less than 1, but it cannot go beyond 1. Okay. Now here I am getting value 3. That is 3. So whatever be the value of this, it doesn't care, and it will choose this one because this is a min node. So from here I am getting 3, I am from here getting 1. So obviously this is to be pruned. Okay. So here with the help of alpha beta pruning, we are able to prune unnecessary branches, that is the branches that have no impact on my final result, right? So at the end, this is my true value and this will be my path. Okay, this will be my path, final path. So this is alpha beta pruning, where we are pruning the unnecessary branches which will have no impact on the final result. Now, time complexity is same as that of, you can say, the pruning does not affect the final result. This means that it gets the exact same result as your min-max algorithm. So it will give you the same result as of your min-max algorithm in your lesser time, right? So the effectiveness of alpha beta pruning is highly dependent on the order in which successor are examined. It's very important. So whatever in order we are examining a successor, it will depend how the pruning will done. For example, in this case, if we begin the exploration not from this branch but from this branch, then obviously we won't be able to prune these branches. Why? Because this is the path. So the order in which we are trying to explore the tree is very much important to find out the successor. In the best case, you can say the search space will be divided by 2, that is order of b to the power d by 2. Okay, and also instead of what b to the power d, this is for the best case scenario. Also, our branching factor will also get reduced. So that was your alpha beta pruning. So in this video lecture, we have discussed about the adversarial search and the 2 types of search, that is your min-max and alpha beta pruning. Thank you.